Welcome to this quiet journey through the cosmos. A gentle exploration designed for those peaceful moments when the day has ended and the night stretches out before you. Wherever you are listening from right now, whether nestled in the comfort of your bed as city lights dim beyond your window, or perhaps sitting in a quiet room as the world outside grows still, I invite you to settle in completely and prepare for a journey unlike any other. Tonight, we will drift together through one of the most profound mysteries in all of physics, exploring the strange and beautiful speed of light, and discovering how this cosmic speed limit bends and breaks everything we thought we understood about reality itself, about time and space and the very fabric of existence. Before we begin, if you enjoy these long, peaceful journeys through science and space, please consider liking this video and subscribing to this little small channel to motivate us to create more of these calming explorations into the wonders of the universe. Let your shoulders drop away from your ears now. Let your jaw unclench if it has been holding tension. Let your breathing slow down to match the rhythm of calm waves touching a distant shore. Feel the surface beneath you supporting your weight entirely, so that you do not have to hold yourself up anymore, so that you can simply exist without effort in this moment. We will take our time with everything tonight, moving slowly like light itself, traveling across the vast emptiness between stars, letting each concept settle into your mind gently before moving on to the next. There is no hurry in the cosmos. Light has been traveling through space for nearly 14 billion years since the Big Bang, and it will continue traveling for trillions more. And in that vast expanse of time, this moment right now is yours to simply be at peace, to let your thoughts become as soft and diffuse as a nebula, to allow yourself to sink deeper into comfort with every breath you take. The constant that changes everything. As we begin our slow drift into the nature of light, let us first appreciate what a strange and wonderful thing it is that light travels at a particular speed at all. For this might seem like an obvious fact, something that requires no explanation. But when we look deeper, we discover that the speed of light is not just another measurement, not just another number to be memorized and forgotten, but is instead a fundamental constant that defines the very structure of our universe. A cosmic speed limit that nothing can exceed and that has profound implications for everything we think we understand about reality. Light travels at approximately 300,000 kilometers per second, or if you prefer to think in miles, about 186,000 miles per second. And while these numbers are impressively large, describing a velocity so great that light could circle the entire Earth more than 7 times in a single second, the true significance of this speed lies not in its magnitude, but in its constancy. In the fact that light always travels at this speed, regardless of who is measuring it or how they are moving. And this constancy, this unchanging nature of light's velocity, is what leads to all the strange and counterintuitive consequences that we will explore together tonight. When we say that light travels at a constant speed, we mean something very specific and very strange. For in our everyday experience, speeds are relative. They depend on the motion of the observer, and this relativity of velocity is so intuitive to us that we barely notice it. If you are standing still and a car drives past you at 50 kilometers per hour, you perceive the car as moving at 50 kilometers per hour. But if you yourself are in a car moving at 30 kilometers per hour in the same direction, then the other car appears to you to be moving at only 20 kilometers per hour. The difference between the two velocities. And this is what we expect, what makes sense based on our everyday experience with moving objects. But light does not behave this way. And this strange behavior was discovered in the late 19th century through a famous experiment conducted by 2 American physicists, Albert Michelson and Edward Morley, who were trying to measure how the motion of Earth through space affects the measured speed of light. They reasoned that if Earth is moving through space, then light traveling in the direction of Earth's motion should appear to move slightly faster, while light traveling in the opposite direction should appear to move slightly slower, just as the car in our example appears to move at different speeds depending on the observer's motion. But when Michelson and Morley performed their careful measurements, they found something completely unexpected. They found that light always traveled at the same speed regardless of Earth's motion, regardless of the direction they measured, regardless of anything. The speed of light was constant, unchanging, the same for all observers no matter how they were moving. And this result was so puzzling, so contrary to common sense and to the expectations of physics at that time, that it took several years for anyone to understand what it meant. The explanation finally came from Albert Einstein in 1905. When he published his special theory of relativity, a revolutionary framework for understanding space and time that took the constancy of light's speed as its foundational principle and derived from it a completely new picture of reality, one in which time can slow down, space can contract, mass and energy are interchangeable, and nothing can travel faster than light. Einstein's insight was to recognize that if the speed of light is constant for all observers, then something else must be flexible, must be able to change, and that something is time and space themselves, the very stage on which all events occur. And this flexibility of time and space is what allows light to always travel at the same speed, no matter who is observing it. Time as a flexible dimension. Let us drift now into one of the most profound and beautiful consequences of light's constant speed. The realization that time itself is not absolute, not a fixed universal clock ticking away the same for everyone everywhere, but is instead flexible, malleable, dependent on motion and gravity, flowing at different rates for different observers depending on their circumstances. This flexibility of time, called time dilation, emerges directly from the constancy of light's speed. And understanding how this works requires us to think carefully about what we mean by measuring time and how light is involved in that measurement. Imagine for a moment a very simple clock, one that consists of two mirrors facing each other with a beam of light bouncing back and forth between them. And each time the light completes one round trip from one mirror to the other and back again. We count that as one tick of the clock. This light clock, as it is called, is not a practical device for everyday timekeeping, but it helps us understand the nature of time in a clear and visual way. Now imagine that this light clock is at rest, stationary relative to you, and you observe the light bouncing directly up and down between the two mirrors, traveling a certain distance with each bounce. And because light always travels at the same speed, the time between ticks is determined simply by the distance between the mirrors divided by the speed of light. But now imagine that this same light clock is moving, carried along by a spaceship flying past you at a significant fraction of the speed of light. And you watch the light clock from your stationary position as it moves past. From your perspective, the light inside the moving clock does not just bounce straight up and down, but must also move sideways to keep up with the mirrors, which are themselves moving horizontally. And so the path of the light forms a diagonal, a longer path than the simple up and down motion you observed when the clock was at rest, because the light must travel a longer path in the moving clock, and because light always travels at the same speed regardless of the motion of its source or observer. The light must take more time to complete each round trip in the moving clock than it does in the stationary clock, and this means that the moving clock ticks more slowly than the stationary clock. Time itself is passing more slowly for the moving clock than for the stationary one. And this is time dilation, the slowing of time due to motion. The crucial point is that this is not an illusion or a trick of perception. It is not that the moving clock merely appears to run slowly, but is actually keeping proper time. Rather, time genuinely passes more slowly for the moving clock. And if there were a person traveling with that clock, they would experience time passing normally from their own perspective. But when they compared their clock to yours after returning from their journey, they would find that less time had passed for them than had passed for you. They would have aged less, experienced fewer moments, lived through a shorter duration, even though from their perspective, everything felt completely normal. This is one of the most startling predictions of special relativity, and it has been confirmed by countless experiments, from precise measurements of atomic clocks flown on airplanes, which show that the moving clocks run slightly slower than stationary clocks on the ground, to observations of particles created in the upper atmosphere by cosmic rays, which travel at speeds close to the speed of light and which live much longer than they would if time were absolute. Their extended lifetimes explained perfectly by time dilation. Time dilation is not a minor effect that only matters in extreme situations. It is a fundamental feature of reality that affects everything, though its effects are only noticeable when velocities approach the speed of light or when gravitational fields are very strong. And in our everyday lives, where we move at speeds far below the speed of light, the effects are too small to notice. But they are always there, always present. A reminder that time is not what we thought it was. The shrinking of space. As we continue our gentle drift through the consequences of light's constant speed, let us now consider what happens to space itself when objects move at velocities approaching the speed of light. For just as time becomes flexible and variable, so too does space undergo a strange transformation, contracting in the direction of motion in a phenomenon called length contraction. This contraction of space is intimately connected to time dilation, both emerging from the same underlying principle, the constancy of light's speed, and both working together to ensure that all observers, regardless of their motion, measure the same speed for light. To understand length contraction, let us return to our example of the light clock. But this time, imagine that instead of the mirrors being oriented vertically, they are oriented horizontally, aligned with the direction of motion, so that as the clock moves, the light bounces back and forth along the direction of travel. From the perspective of someone traveling with the clock, the light simply bounces back and forth between the two mirrors, just as it did in the vertical orientation. And the time between ticks is determined by the distance between the mirrors and the speed of light. But from the perspective of a stationary observer watching the clock move past, something interesting happens. For if space were absolute and unchanging, we would expect the light to take different amounts of time to travel in the forward direction, where it must catch up to the front mirror, which is moving away, and in the backward direction, where it moves toward the rear mirror, which is moving toward it. And these different travel times would mean that the moving clock would not tick at the same rate as a stationary clock, contradicting what we know about time dilation from our previous example with the vertical light clock. The resolution to this apparent contradiction is that space itself must contract in the direction of motion. The distance between the mirrors must become shorter when measured by the stationary observer than when measured by someone moving with the clock. And this contraction of space precisely compensates for the effects of motion, such that the light takes exactly the right amount of time to complete each round trip, consistent with the time dilation we expect. The amount of length contraction depends on how fast the object is moving, with faster speeds producing greater contraction, and at the speed of light itself, which nothing with mass can actually reach. Lengths would contract to zero in the direction of motion. The entire universe would appear compressed into a single point along the direction of travel. though of course no material object can achieve this because it would require infinite energy. For velocities much smaller than the speed of light, the contraction is negligible, too small to notice in everyday life. But as speeds increase toward the cosmic speed limit, the effects become dramatic, and a spaceship traveling at 90% the speed of light would appear to a stationary observer to be compressed to less than half its length in the direction of travel. Though to the occupants of the spaceship, everything would appear normal. It is the outside universe that would appear compressed along their direction of motion. This symmetry, this reciprocal nature of length contraction and time dilation, where each observer sees the other's space contracted and time dilated, is one of the beautiful and sometimes confusing aspects of special relativity. For it shows that there is no absolute standard of rest, no privileged reference frame from which to judge motion. Each observer's perspective is equally valid, and the phenomena they observe are real, not illusions, even though different observers measure different values for the same quantities. The cosmic speed limit. Let us drift now to consider why nothing can travel faster than light. Why this particular speed represents an absolute limit beyond which no material object or signal can go. And what this cosmic speed limit tells us about the structure of the universe. The impossibility of exceeding the speed of light emerges from Einstein's famous equation relating energy and mass, E equals mc squared, which tells us that energy and mass are interchangeable, that mass is a concentrated form of energy, and that adding energy to an object increases not just its kinetic energy, its energy of motion, but also its effective mass, making it harder to accelerate further. When an object is at rest, it has a certain rest mass, the intrinsic mass it possesses simply by virtue of being that particular type of object. An electron has a rest mass, a proton has a different rest mass, and so on. When we give the object energy by accelerating it, pushing it to higher speeds, that energy becomes part of the object's total mass energy. And as the object approaches the speed of light, the amount of energy required to accelerate it further increases without limit, approaching infinity as the speed approaches the speed of light. And this means that no finite amount of energy can ever accelerate a massive object all the way to the speed of light, let alone beyond it. Only particles with zero rest mass, like photons, the particles of light itself, can travel at the speed of light. And they do so not by accelerating to that speed, but by always moving at that speed. It is their natural state, the only speed at which they can exist, and they can never be slowed down or stopped. They simply are light speed. This cosmic speed limit is not a limitation of technology or engineering, not something that might be overcome with better rockets or more powerful engines, but is instead a fundamental feature of the universe, woven into the very fabric of space-time itself. And any attempt to exceed it would require infinite energy and would violate the basic principles of physics as we understand them. The speed of light is fast by human standards, fast enough to circle the Earth multiple times in a second. But on cosmic scales, it is agonizingly slow. The universe is so vast that even light takes billions of years to traverse it. The most distant galaxies we can observe are so far away that their light has been traveling toward us for over 13 billion years, nearly the entire age of the universe. And we see them not as they are now, but as they were in the ancient past when that light was emitted. This slowness of light on cosmic scales creates a kind of horizon, a limit to how far we can see and how much of the universe is accessible to us. For there are regions of space so distant that their light has not had time to reach us yet since the beginning of the universe. And if the expansion of the universe continues to accelerate as observations suggest, there are regions that we will never be able to see, no matter how long we wait, because they are receding from us faster than light can travel toward us. Not because anything is moving through space faster than light, which would violate special relativity, but because space itself is expanding, carrying distant galaxies away from us. And the expansion of space is not limited by the speed of light. The cosmic speed limit, thus, has profound implications, not just for how fast things can move, but for the very structure of the observable universe, for what is knowable and what must remain forever beyond our reach. Simultaneity and the relativity of now. As we drift deeper into the strange world that emerges from the constancy of light speed, let us now consider one of the most philosophically challenging consequences of special relativity: the relativity of simultaneity. The realization that events that appear simultaneous to one observer may not be simultaneous to another. That the very concept of now is not absolute, but depends on the motion of the observer, and that there is no universal present moment that extends throughout the universe. To understand this, imagine two events occurring at different locations in space. Perhaps two stars exploding as supernovae, one star located to your left and one to your right. And imagine that the light from both explosions reaches you at the same instant, arriving at your eyes simultaneously. From your perspective, having received the light from both events at the same time, and knowing that light travels at a constant speed, you might conclude that the two explosions must have occurred simultaneously, that there was a single moment in time when both stars exploded. And this conclusion seems reasonable and natural. But now imagine that there is another observer moving rapidly relative to you, perhaps traveling in a spaceship moving from left to right at a significant fraction of the speed of light. And this moving observer also witnesses both explosions. But because they are moving toward the right, they will encounter the light from the right-hand supernova before they encounter the light from the left-hand supernova. And when they analyze the data, taking into account their motion and the distances involved and the finite speed of light, they will conclude that the right-hand supernova occurred first, that it was not simultaneous with the left-hand supernova, and that there was a time interval between the two events. Both observers are correct within their own reference frames. Both have made valid measurements and drawn valid conclusions, and yet they disagree about whether the events were simultaneous. And this disagreement is not due to any error or miscalculation, but is a fundamental feature of reality, a consequence of the fact that space and time are interwoven into a single four-dimensional continuum called space-time, and that different observers slice this continuum into space and time in different ways depending on their motion. The relativity of simultaneity means that there is no absolute ordering of events that are separated in space, no universal timeline that applies to the entire cosmos. And this has profound implications for how we think about causality and the structure of reality. Events that are causally connected, where one event directly influences another, do have an absolute ordering that all observers agree on. The cause always precedes the effect regardless of the observer's motion. But events that are not causally connected, that are so far apart that light could not travel from one to the other in the time between them, can be ordered differently by different observers, with one observer seeing event A before event B, while another observer sees event B before event A. And both perspectives are equally valid. This might seem paradoxical or impossible, but it is a direct mathematical consequence of the Lorentz transformations, the equations that relate the measurements of space and time made by different observers moving relative to each other. And these equations have been tested exhaustively and confirmed to extraordinary precision by countless experiments. The relativity of simultaneity challenges our intuitive notion of time as a universal flowing river that carries all events along in a single coordinated stream. And it replaces this notion with a more subtle picture in which each observer has their own personal sense of now that extends through space according to their motion. And different observers' nows slice through space-time at different angles, overlapping in some regions and diverging in others. The twin paradox and time travel let us now explore one of the most famous thought experiments in special relativity, the twin paradox, which illustrates the strange consequences of time dilation in a particularly vivid way and raises questions about the nature of time and the possibility of time travel into the future. Imagine two twins, one who stays on Earth and one who travels on a spaceship to a distant star and back, moving at a velocity close to the speed of light. And when the traveling twin returns home, they find that they have aged less than their sibling who stayed on Earth. That less time has passed for them during their journey than has passed for their twin. And so, they are now younger than their identical twin, perhaps by years or decades, depending on the speed and duration of the journey. This prediction of special relativity has been confirmed experimentally using precise atomic clocks. And it is not a controversial or debatable aspect of the theory, but a well-established fact, yet it is often called a paradox because there seems to be a symmetry that makes the situation contradictory. From the perspective of the traveling twin, it might seem that they could consider themselves to be at rest and the Earth to be moving away and then returning. And by the same logic, shouldn't it be the Earth-bound twin who ages less? The resolution to this apparent paradox is that the situation is not actually symmetric. For the traveling twin must accelerate and decelerate, must turn around at the distant star and change direction. And these accelerations break the symmetry, making the traveling twin's experience fundamentally different from the Earth-bound twin's experience. And it is the traveler who experiences less time, who genuinely ages less, who lives through fewer moments between departure and return. The twin paradox is not just a theoretical curiosity, but demonstrates a real form of time travel into the future. For the traveling twin has effectively jumped forward in time, relative to their sibling and to everyone on Earth. They have skipped over years or decades by traveling at high speed. And when they return, they find that the world has moved on without them, that people they knew are older or gone, that technology has advanced, that history has progressed, all while they experienced only the relatively short duration of their journey. This is one-way time travel, moving only forward into the future and never backward into the past. And it is allowed by special relativity. Indeed, it is inevitable for anyone who moves at speeds approaching the speed of light. But travel into the past, returning to earlier moments, remains problematic and may be impossible, at least within the framework of special relativity. Though more complex scenarios involving general relativity and exotic space-time geometries like wormholes and rotating black holes have been proposed as potential mechanisms for backward time travel. Though all such proposals involve assumptions and conditions that may not be physically realistic or achievable. The twin paradox also raises philosophical questions about personal identity and the nature of lived experience. For the two twins, who began as identical and experienced the same amount of time from birth until the journey began, have now lived through different durations, have had different amounts of subjective experience, have different total ages, and yet they meet again, standing side by side, one younger than the other. And this difference is real and physical, not a matter of perception or convention. The traveling twin has literally experienced less time than their sibling, has had fewer heartbeats, fewer breaths, fewer thoughts. And this discrepancy can never be reconciled, can never be made to even out. The lost time is gone forever, or rather, it never existed for the traveler, was skipped over by their high-speed journey through space. Mass energy, and E equals mc squared. As we drift through the landscape of relativistic physics, let us turn our attention to perhaps the most famous equation in all of science. E equals mc squared, Einstein's elegant statement that energy and mass are interchangeable, that they are different forms of the same underlying quantity, and that any mass can in principle be converted into energy and vice versa. With the speed of light squared serving as the conversion factor, this equation, which emerged from Einstein's special theory of relativity, reveals a profound unity in nature, showing that matter and energy are not fundamentally different kinds of things, but are aspects of a single entity that can manifest in different ways. And this insight has had enormous practical and theoretical consequences, from explaining how the sun generates its energy through nuclear fusion, to enabling the development of nuclear weapons and nuclear power, to providing a framework for understanding particle physics and the creation and annihilation of matter. The c² factor in the equation, where c represents the speed of light, is an enormous number, approximately 9 times 10 to the power of 16 when expressed in meters squared per second squared, and this huge factor means that even a tiny amount of mass is equivalent to an enormous amount of energy. A single gram of matter, if completely converted to energy, would release about 90 trillion joules, equivalent to the energy of about 20,000 tons of TNT, the explosive yield of a small nuclear weapon. This is why nuclear reactions, both fission and fusion, are so powerful, because they convert a small fraction of mass into energy. And even though the fraction is small, usually less than 1% of the total mass, the resulting energy release is enormous because of the c² factor. The interchangeability of mass and energy also means that when we add energy to an object, we are actually increasing its mass. Though for ordinary energies and velocities, this increase is imperceptibly small. But as speeds approach the speed of light, the kinetic energy becomes comparable to the rest mass energy and the object's total energy, and therefore its effective mass increases dramatically, which is why it becomes progressively harder to accelerate the object further. As we discussed earlier in the context of the cosmic speed limit, at the speeds of everyday life, the mass increase due to motion is utterly negligible. A car moving at highway speeds has a kinetic energy that increases its mass by a minuscule fraction, far too small to measure or notice. But particles and accelerators traveling at 99.99% the speed of light, or faster, have effective masses that are thousands of times their rest masses, and the energy required to accelerate them further increases enormously, making it effectively impossible to reach the speed of light no matter how much energy is invested. E equals mc² also explains how particles can be created from pure energy. For if energy and mass are equivalent, then sufficiently concentrated energy can spontaneously transform into particle-antiparticle pairs, matter and antimatter, springing into existence from the energy field. And this process, called pair production, is routinely observed in particle physics experiments and is also thought to have occurred in the early universe, when temperatures and energy densities were high enough that particles and antiparticles were constantly being created and annihilated, maintaining a kind of equilibrium between matter and energy. The equation works in both directions. Energy can become mass, and mass can become energy. And this symmetry is fundamental to our understanding of the universe, explaining not just nuclear reactions and particle physics, but also the energy content of empty space itself. For even the vacuum, even apparently empty space, has energy associated with it due to quantum fluctuations. And this vacuum energy contributes to the total energy budget of the universe, and may be related to the mysterious dark energy that is driving the accelerated expansion of the cosmos. Photons, and the quantum nature of light. Let us drift now into the quantum nature of light, for we have been treating light as a wave traveling at a constant speed. But light also behaves as a stream of particles called photons. And understanding this dual nature, this wave-particle duality, is essential to fully appreciating what light is and how it interacts with matter. The quantum nature of light was discovered in the early 20th century through a series of experiments and theoretical insights that showed that light is not simply a continuous wave, as had been thought since the time of Maxwell, but is instead quantized, meaning it comes in discrete packets or quanta, each quantum being a photon, a particle of light carrying a specific amount of energy that depends on its frequency. The energy of a photon is given by the equation E equals h times F, where E is energy, h is Planck's constant, a fundamental constant of nature that sets the scale of quantum effects, and F is the frequency of the light. And this equation tells us that higher frequency light, such as blue or ultraviolet light, consists of photons with more energy per photon than lower frequency light, like red or infrared. And this is why ultraviolet light can cause sunburn and damage DNA, while red light cannot. The individual photons of ultraviolet light carry enough energy to break chemical bonds, while photons of red light do not. Photons are massless particles that always travel at the speed of light. They can never be at rest and can never move slower than c. And when a photon is created, say by an electron dropping to a lower energy level in an atom, it immediately moves away at the speed of light. And when it is absorbed by another atom, it is completely destroyed, its energy transferred to the absorbing atom. There is no such thing as a stationary photon or a slow photon, only photons moving at light speed. Despite being massless, photons do carry momentum, and this momentum is given by P equals E divided by C, which can also be written as PAC equals H divided by lambda, where lambda is the wavelength of the light, and this momentum means that light can exert pressure on objects, can push things. And though the pressure from ordinary light sources is extremely small, too small to notice in everyday life, it can be significant in space where there is no air resistance. And proposals have been made to use solar sails, large reflective surfaces that catch sunlight and are pushed by the momentum of photons to propel spacecraft across the solar system, a form of propulsion that requires no fuel, only sunlight. The dual nature of light, its ability to behave as both a wave and a particle, is not a contradiction, but a fundamental feature of quantum mechanics. All quantum objects exhibit this duality, sometimes appearing wave-like and sometimes appearing particle-like, depending on how we observe them, and which aspect we see depends on what kind of measurement we make. When we measure light in ways that probe its wave properties, such as observing interference patterns in a double-slit experiment, we see wave behavior. But when we measure it in ways that probe its particle properties, such as detecting individual photons with a photomultiplier tube, we see particle behavior, and neither description is more correct or more fundamental than the other. Both are necessary to fully understand light, and the mathematics of quantum mechanics seamlessly incorporates both aspects into a single unified framework. The quantum nature of light also leads to strange phenomena that have no classical analog, such as quantum entanglement, where two photons can be connected in such a way that measuring the properties of one instantly affects the properties of the other, no matter how far apart they are. A phenomenon that Einstein famously called spooky action at a distance, and that has been experimentally verified many times, confirming that the quantum world operates according to rules that are fundamentally different from those of our everyday macroscopic experience. Space-time as a unified fabric. As we continue our gentle drift through relativity, let us now consider the deeper conceptual shift that Einstein's theories represent, the understanding that space and time are not separate independent entities, but are aspects of a single unified four-dimensional continuum called space-time. And that the division of this continuum into space and time is not absolute, but depends on the motion of the observer. In classical physics, before relativity, space was imagined as a three-dimensional stage, a fixed background extending infinitely in all directions. And time was imagined as a separate one-dimensional parameter, a universal clock ticking away uniformly for everyone everywhere, and events occurred at specific locations in space at specific moments in time. And all observers agreed on which events were simultaneous and on the duration of time intervals between events. But special relativity showed that this picture is wrong, that space and time are intimately connected, that measurements of distance and measurements of duration are intertwined, and that different observers moving relative to each other will disagree about both spatial separations and temporal separations between events. Yet all observers will agree on a certain combination of space and time called the space-time interval, which is a kind of four-dimensional distance that remains invariant, unchanged, regardless of the observer's motion. This space-time interval is calculated using the equation s squared equals c squared t squared minus x squared, where t is the time difference between two events and x is the spatial distance between them. And the fact that this quantity is the same for all observers means that space-time itself is the fundamental reality, and that the split into separate space and time is just one way of looking at this four-dimensional structure, a way that depends on the observer's state of motion. The concept of space-time was developed by Hermann Minkowski, who was Einstein's mathematics professor, and who recognized that the Lorentz transformations of special relativity could be understood geometrically as rotations in a four-dimensional space with an unusual metric. And Minkowski famously declared that, henceforth, space by itself and time by itself are doomed to fade away into mere shadows. And only a kind of union of the two will preserve an independent reality. And this unification of space and time into space-time is one of the most profound conceptual shifts in the history of science, comparable to the realization that the Earth is not the center of the universe or that biological species evolve through natural selection. In space-time, events are points, not just locations in space, but combinations of where and when. And the history of an object traces out a path through space-time called a world line, a continuous curve that shows where the object is at each moment of time. And this world line is the object's complete history from past to future, all laid out in the four-dimensional space-time structure. Light itself travels along special world lines called null geodesics, or light cones, surfaces in space-time that divide events into three categories relative to any given event. Events in the past, light cone are events that could have influenced the given event by sending light or other signals that arrive at or before the event. Events in the future, light cone, are events that could be influenced by the given event. And events outside the light cone are space-like, separated from the given event, meaning no signal traveling at or below the speed of light could connect them. And these events have no absolute temporal ordering. Different observers can disagree about which occurs first. The light cone structure of space-time, with its division of events into causally connected and causally disconnected regions, is fundamental to understanding how cause and effect work in relativity. And it provides a geometric way of visualizing why nothing can travel faster than light. For any world line that traveled faster than light would have to cross from inside the light cone to outside it, connecting events that are space-like separated. And this would lead to paradoxes involving causality and would allow effects to precede their causes in some reference frames, violating the logical structure of cause and effect. General relativity and curved spacetime. Let us drift now from special relativity, which deals with inertial reference frames, observers moving at constant velocity relative to each other, to general relativity. Einstein's theory of gravity that extends the ideas of special relativity to include acceleration and gravitational fields. And that describes gravity not as a force acting through space, but as a curvature of space-time itself. A warping of the four-dimensional fabric that causes objects to follow curved paths that we interpret as the effects of gravitational attraction. The key insight of general relativity is the equivalence principle, the observation that acceleration and gravity are locally indistinguishable, that an observer in an accelerating elevator far from any gravitational field would experience effects identical to an observer at rest in a gravitational field. And conversely, an observer in free fall in a gravitational field would experience weightlessness identical to an observer floating in deep space far from any masses. This equivalence suggests that acceleration and gravity are manifestations of the same underlying phenomenon. And Einstein realized that this phenomenon could be understood geometrically as a curvature of space-time, with massive objects like stars and planets warping the space-time around them, and freely falling objects, including objects that we think of as being in orbit, simply following the straightest possible paths through this curved space-time, paths called geodesics, just as light follows geodesics called null geodesics. In flat space-time, the space-time of special relativity that applies in regions far from massive objects, geodesics are straight lines. Objects moving at constant velocity follow straight paths through space. But in curved space-time, geodesics are curved, and objects following geodesics appear to us to be accelerating, changing direction, falling toward massive bodies. And this apparent acceleration is what we call gravity. But from the perspective of general relativity, the object is not actually accelerating in the sense of feeling a force. It is simply following the natural path through curved space-time. And it is we, standing on the surface of Earth, who are being accelerated, pushed upward by the ground beneath us to prevent us from following our natural geodesic path, which would take us falling toward the center of Earth. The curvature of space-time is determined by the distribution of mass and energy through Einstein's field equations, a set of 10 coupled nonlinear partial differential equations that relate the curvature of space-time to the stress-energy tensor, a mathematical object that describes the density and flux of energy and momentum in space-time. And solving these equations for a given distribution of mass and energy tells us how space-time is curved and therefore how objects will move and how light will propagate in that region. The field equations are notoriously difficult to solve except in highly symmetric cases. But several important exact solutions have been found, including the Schwarzschild solution, which describes the space-time around a non-rotating spherical mass like a star or black hole, and the Kerr solution, which describes rotating black holes, and the Friedmann-Robertson-Walker solution, which describes the expanding universe as a whole. General relativity predicts numerous phenomena that have been observationally confirmed, including the bending of light by gravity, called gravitational lensing, where light from distant stars or galaxies is deflected as it passes near massive objects like the Sun or galaxy clusters, creating distorted images and sometimes multiple images of the same background object. And this effect was first confirmed during a solar eclipse in 1919, when stars near the Sun's position in the sky appeared shifted compared to their positions when the Sun was elsewhere, confirming Einstein's prediction and making him world famous overnight. General relativity also predicts the existence of black holes, regions where space-time is so severely curved that nothing, not even light, can escape once it crosses a boundary called the event horizon. And black holes have been detected indirectly through their effects on nearby matter, and more recently directly through gravitational wave observations of merging black holes. and through images of the shadows cast by supermassive black holes at the centers of galaxies. Gravitational time dilation. As we drift deeper into the consequences of general relativity, let us explore how gravity affects the flow of time, producing a phenomenon called gravitational time dilation that is similar in some ways to the time dilation caused by motion in special relativity, but that arises from a different physical mechanism, the curvature of space-time rather than relative velocity. Gravitational time dilation means that time passes more slowly in stronger gravitational fields. Clocks run slower when they are closer to massive objects than when they are farther away. And this effect, though usually small, has been precisely measured and is essential to the operation of technologies like GPS satellites, which must account for gravitational time dilation to maintain accurate positioning. To understand gravitational time dilation, we can think about the equivalence principle, which tells us that acceleration and gravity are locally equivalent. And we can imagine an elevator accelerating upward in deep space, far from any gravitational fields. And inside this elevator, an observer sends a beam of light from the floor to the ceiling. And by the time the light reaches the ceiling has moved upward due to the acceleration. And so from the perspective of someone outside the elevator, watching it accelerate, the light appears to have been Doppler shifted to a lower frequency, redshifted, because the ceiling is moving away from the source of the light at the floor. Now, by the equivalence principle, this same effect must occur in a gravitational field. Light traveling upward in a gravitational field, away from the massive object creating the field, must be redshifted, losing energy. And since the energy of a photon is proportional to its frequency, the decrease in energy corresponds to a decrease in frequency. And this gravitational redshift is exactly equivalent to time dilation. For if the frequency of light is lower, then the oscillations that define that frequency are taking longer. Time is running slower, and this slowing of time is proportional to the strength of the gravitational field. The closer to a massive object, the slower time runs. This gravitational time dilation has been confirmed experimentally many times, beginning with the Pound-Rebka experiment in 1959, which measured the gravitational redshift of gamma rays traveling up and down a tower at Harvard University, detecting the tiny frequency shift predicted by general relativity. And more recently, atomic clocks have been used to measure gravitational time dilation between clocks at different altitudes, confirming that clocks at higher altitudes, where the gravitational field is slightly weaker, run faster than clocks at lower altitudes. And the effect is precisely as predicted by general relativity. GPS satellites orbit at about 20,000 kilometers above Earth's surface, where the gravitational field is weaker than at the surface, and the clocks on the satellites run faster than clocks on the ground by about 45 microseconds per day due to gravitational time dilation. And if this effect were not corrected for, GPS positioning would rapidly become inaccurate, accumulating errors of several kilometers per day. But by adjusting the satellite clocks to compensate for gravitational time dilation, as well as for the time dilation due to their orbital motion, which makes them run slower, GPS maintains its accuracy, a practical everyday application of general relativity. Gravitational time dilation also has more exotic consequences near very massive or very compact objects. Near the event horizon of a black hole, for example, where the gravitational field is extremely strong, time dilation becomes extreme, and an outside observer watching something fall toward the event horizon would see it slow down, its motion appearing to freeze as it approaches the horizon, and light emitted from the falling object would be redshifted to longer and longer wavelengths, fading and disappearing. Though from the perspective of the falling object itself, time would pass normally, and it would cross the horizon in a finite amount of its own time. experiencing nothing special at the moment of crossing. The apparent freezing and fading being artifacts of the extreme time dilation between the outside observer and the falling object. Gravitational waves and ripples in space-time. Let us turn our attention now to one of the most beautiful predictions of general relativity: the existence of gravitational waves, ripples in the fabric of space-time itself that propagate outward from accelerating masses at the speed of light, carrying energy and information about cosmic events like colliding black holes and neutron stars. And these gravitational waves provide a completely new way of observing the universe, complementary to traditional electromagnetic observations using light and other forms of radiation. Gravitational waves arise because changes in the distribution of mass and energy, particularly accelerations of massive objects, create disturbances in space-time curvature that propagate outward as waves, similar to how accelerating electric charges create electromagnetic waves. And just as electromagnetic waves consist of oscillating electric and magnetic fields, gravitational waves consist of oscillating curvature, alternately stretching and compressing space in perpendicular directions as the wave passes through. And any object or measuring device in the path of a gravitational wave will experience these oscillating stretches and compressions, though the effects are extraordinarily small for all but the most violent cosmic events. Einstein himself was uncertain about whether gravitational waves were real or were artifacts of the mathematical formalism of general relativity. And it was not until decades after his initial work that the reality of gravitational waves was firmly established theoretically. And it took another several decades before they were detected directly. The first indirect evidence for gravitational waves came from observations of a binary pulsar system, two neutron stars orbiting each other, discovered in 1974 by Russell Hulse and Joseph Taylor. And careful measurements of this system over many years showed that the orbital period was decreasing. The two neutron stars were gradually spiraling closer together, and the rate of this orbital decay matched precisely the prediction for energy loss due to gravitational wave emission, providing compelling indirect evidence that gravitational waves are real and carry energy away from the system exactly as general relativity predicts. The first direct detection of gravitational waves came in September of 2015, when the LIGO observatories, two large laser interferometers located in Louisiana and Washington State, simultaneously detected the signal from two black holes, each about 30 times the mass of the Sun, spiraling together and merging into a single larger black hole over 1 billion light-years away. And the gravitational wave signal, which lasted only a fraction of a second and caused the arms of the interferometers to change length by less than 1,000th the diameter of a proton, matched the predictions of general relativity with remarkable precision, allowing physicists to extract detailed information about the masses and spins of the merging black holes and about the properties of the final merged black hole. This detection, announced in February of 2016, was a triumph for experimental physics and for general relativity, confirming a century-old prediction and opening a new window on the universe. And since then, many more gravitational wave detections have been made. From additional black hole mergers, from the merger of two neutron stars, which was also observed in electromagnetic radiation across the spectrum, providing a wealth of information about the physics of these extreme events, and from other exotic sources. Gravitational waves travel at the speed of light, as they must, according to general relativity, for they are disturbances in space-time itself. And this means that when we detect gravitational waves from a distant source, we are observing an event that occurred in the past. The gravitational waves have been traveling toward us for the time it takes light to cover the distance. And just as with light, we cannot see the present state of distant objects, but only their past. The universe beyond our immediate vicinity is revealed to us only through signals that have traveled at the speed of light or slower. And the farther away we look, the farther back in time we see. A consequence of the finite speed of light and other signals that creates a deep connection between space and time, between distance and history, making astronomy inherently a study of the past. The light barrier and causality. Let us drift now into deeper contemplation of why the speed of light functions as an absolute speed limit, and what this means for causality, the principle that causes must precede their effects, and how the constancy of light speed and the structure of space-time work together to ensure that the logical flow of cause and effect is preserved throughout the universe. One of the most fundamental aspects of our experience of reality is that causes come before effects. We drop a glass and then it breaks. We flip a switch and then the light turns on. We speak and then someone hears us. And this temporal ordering of cause and effect seems so obvious and necessary that we rarely question it. But in special relativity, where different observers can disagree about whether distant events are simultaneous, we might worry that they could also disagree about which event caused which. That one observer might see a cause followed by its effect, while another observer sees the effect followed by the cause. And this would be paradoxical and would undermine the logical structure of the universe. The reason this paradox does not occur is because of the light cone structure we discussed earlier. Events that are causally connected, where one can influence the other by sending a signal, are always separated by a time-like interval, meaning they lie within each other's light cones. And for such events, all observers agree on their temporal ordering. The cause always comes before the effect, regardless of the observer's motion. Events that are space-like separated, outside each other's light cones, cannot be causally connected because no signal traveling at or below the speed of light can get from one to the other. And it is only for these causally disconnected events that different observers can disagree about temporal ordering. But this disagreement does not create any paradox because there is no causal relationship between the events, neither influences the other. And so the order in which they occur is physically meaningless, a matter of perspective rather than objective reality. The cosmic speed limit of light is what ensures this structure. For if signals could travel faster than light, if information or influence could propagate superluminally, then it would be possible to send a signal from one event to another event that is space-like separated from it, connecting events outside each other's light cones and in some reference frames. This signal would appear to travel backward in time, arriving before it was sent. And this would create genuine causal paradoxes where effects could precede their causes. To see this more clearly, imagine a hypothetical faster-than-light signal sent from Earth to a distant star, arriving almost instantaneously from Earth's perspective. And imagine that the star immediately sends a similar faster-than-light signal back to Earth. And depending on the relative motion of Earth and the star, there are reference frames in which the return signal arrives at Earth before the original signal was sent, creating a closed loop in time where the signal is its own ancestor, and allowing all sorts of logical contradictions like the famous grandfather paradox, where someone travels back in time and prevents their own birth. The impossibility of faster-than-light travel and communication is thus intimately connected to the preservation of causality, to maintaining the logical consistency of cause and effect. And this connection suggests that the speed of light is not just an arbitrary limit, but is deeply woven into the structure of the universe, a fundamental feature of how reality is organized. Some physicists have speculated about ways to circumvent the light barrier, usually involving exotic space-time geometries like wormholes that connect distant regions of space through shortcuts, or hypothetical particles called tachyons that would always travel faster than light and never slower. But all such ideas face severe theoretical difficulties and may ultimately be impossible. The universe may simply not allow them. And if they were possible, they would likely lead to causal paradoxes that would need to be resolved through some mechanism we do not currently understand. Perhaps quantum mechanics or some deeper theory that we have not yet discovered. The Doppler effect and redshift. As we continue our gentle drift through the physics of light, let us explore the Doppler effect. The change in frequency and wavelength of light due to the relative motion between the source of the light and the observer, a phenomenon that is familiar from everyday experience with sound, where the pitch of a siren appears higher as an ambulance approaches and lower as it recedes. And that plays a crucial role in astronomy, where it is used to measure the velocities of stars and galaxies and to study the expansion of the universe. The Doppler effect for light works in a similar way to the Doppler effect for sound, but with some important differences due to the constancy of the speed of light and the effects of special relativity. When a source of light is moving toward an observer, the light is shifted to shorter wavelengths and higher frequencies, a phenomenon called blue shift because visible light shifts toward the blue end of the spectrum, though the effect applies to all wavelengths of electromagnetic radiation, not just visible light. Conversely, when the source is moving away from the observer, the light is shifted to longer wavelengths and lower frequencies, called redshift. And the amount of the shift depends on the velocity of the source relative to the observer, with faster velocities producing larger shifts. For velocities that are small compared to the speed of light, the Doppler formula is relatively simple. The fractional change in wavelength is approximately equal to the velocity divided by the speed of light. But for velocities approaching the speed of light, the full relativistic Doppler formula must be used, which includes factors that account for time dilation. And as the velocity approaches the speed of light, the redshift becomes extreme. Wavelengths can be stretched by factors of hundreds or thousands, and light that was originally in the visible spectrum can be shifted all the way into the infrared or even radio wavelengths. In astronomy, the Doppler effect is used extensively to measure the radial velocities of stars and galaxies, how fast they are moving toward or away from us. And this information is crucial for understanding the dynamics of galaxies, the orbits of binary stars, the rotation of planets, and many other phenomena. One of the most important applications of the Doppler effect is in cosmology, where it is used to measure the redshifts of distant galaxies. And it was through measuring these redshifts that Edwin Hubble discovered in the 1920s that the universe is expanding, that distant galaxies are receding from us with velocities proportional to their distances, a relationship now known as Hubble's law. And this expansion is not due to galaxies moving through space away from us, but is due to space itself expanding, carrying galaxies along with it. And this cosmic expansion redshifts the light from distant galaxies, stretching the wavelengths as the light travels through expanding space. And the farther away a galaxy is, the longer its light has been traveling through expanding space, and the more its wavelengths have been stretched, producing larger redshifts for more distant galaxies. The redshifts of galaxies provide a measure of how much the universe has expanded since the light was emitted. A redshift of 1 means the universe has doubled in size since the light began its journey. A redshift of 2 means it has tripled in size, and so on. And by measuring the redshifts of many galaxies at different distances, cosmologists can map out the expansion history of the universe and test models of how the expansion has evolved over time. Whether it has been slowing down due to gravity or speeding up due to dark energy. And observations indicate that the expansion is currently accelerating, driven by the mysterious dark energy that makes up about 70% of the total energy content of the universe. The cosmic microwave background. and the early universe. Let us drift now to one of the most important observations in all of cosmology: the cosmic microwave background radiation, a faint glow of light that fills all of space and that is the cooled remnant of the intense heat of the Big Bang, providing a snapshot of what the universe looked like when it was only about 380,000 years old, long before any stars or galaxies had formed. The cosmic microwave background was predicted theoretically in the 1940s by George Gamow and his colleagues, who realized that if the universe began in a hot, dense state and has been expanding and cooling ever since, then there should be a remnant of that early heat still present today, redshifted by the expansion to microwave wavelengths. And this prediction was confirmed in 1965 when Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs, detected a persistent noise in their antenna that was the same in all directions and that corresponded to a temperature of about 3 degrees above absolute zero. And they eventually realized that this noise was the cosmic microwave background, the echo of the Big Bang. And their discovery earned them the Nobel Prize in Physics. The cosmic microwave background is remarkably uniform, having almost exactly the same temperature in all directions to better than 1 part in 100,000. And this uniformity tells us that the early universe was extraordinarily homogeneous, with only tiny variations in density and temperature. And these tiny variations are crucially important because they were the seeds from which all structure in the universe eventually grew. The slight overdensities attracting more matter through gravity and eventually collapsing to form galaxies and clusters of galaxies, while the underdense regions remained mostly empty, becoming the voids between galaxy clusters. Detailed observations of the cosmic microwave background by satellites like COBE, WMAP, and Planck have mapped the tiny temperature variations across the sky with exquisite precision. And by analyzing the statistical properties of these variations, cosmologists have been able to determine many fundamental parameters of the universe with remarkable accuracy, including its age, about 13.8 billion years, its geometry, which is flat or very nearly flat, its composition, about 5% ordinary matter, about 27% dark matter, and about 68% dark energy, and the properties of the primordial density fluctuations that seeded structure formation. The cosmic microwave background also provides evidence for inflation, a hypothetical period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang, during which the universe expanded by an enormous factor, smoothing out irregularities and creating the uniformity we observe, while simultaneously amplifying quantum fluctuations to macroscopic scales, creating the seeds of structure and the pattern of temperature variations in the cosmic microwave background. Matches the predictions of inflation remarkably well, though inflation remains a hypothesis, not a confirmed theory, and alternative explanations for the observations are still being explored. The cosmic microwave background is also a beautiful example of how the finite speed of light connects us to the past. For when we observe the cosmic microwave background, we are seeing light that has been traveling toward us for nearly 14 billion years. We are looking back in time to the surface of last scattering, the moment when the universe became transparent and photons could travel freely. And everything we observe at greater distances, in earlier cosmic times, is hidden from us because the universe was opaque before that moment, filled with a hot plasma that absorbed and scattered light. And so the cosmic microwave background represents a kind of horizon, the farthest back in time we can see using electromagnetic radiation. Though in principle, we could observe even earlier epochs using other messengers like neutrinos or gravitational waves which can travel through the opaque early universe, black holes, and the ultimate speed limit. Let us drift now towards some of the most extreme objects in the universe, Black holes. Regions where space-time is so severely curved that nothing, not even light, can escape. And where the concepts of space and time break down in ways that challenge our understanding of physics and reality. Black holes form when very massive stars exhaust their nuclear fuel and collapse under their own gravity, compressing their mass into a volume so small that the escape velocity, the speed needed to escape the gravitational pull, exceeds the speed of light. And once this happens, a black hole is created, surrounded by an event horizon, a boundary in space-time beyond which events cannot affect an outside observer, because any signal would need to travel faster than light to escape. The radius of the event horizon is called the Schwarzschild radius, named after Carl Schwarzschild, who found the first exact solution to Einstein's field equations, describing a black hole. And this radius depends only on the mass of the black hole. Larger masses producing larger event horizons. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers, while for a supermassive black hole with 1 billion solar masses like those found at the centers of large galaxies, the Schwarzschild radius is about 1 billion kilometers, roughly the distance from the Sun to Jupiter. Despite their name and their representation in popular culture, black holes are not cosmic vacuum cleaners that suck in everything around them. They have the same gravitational pull as any other object of the same mass. And if the Sun were suddenly replaced by a black hole of equal mass, Earth's orbit would not change, though Earth would become very cold and dark. What makes black holes special is not their gravitational strength at large distances, but the extreme curvature of space-time near the event horizon, and the fact that once something crosses the event horizon, it can never come back out or send any signal out. It is forever trapped, destined to fall toward the singularity at the center of the black hole. The singularity is a point where space-time curvature becomes infinite, where general relativity breaks down and predicts its own failure. And what actually happens at the singularity is unknown. It may be that quantum gravity, a theory that combines general relativity and quantum mechanics and that we do not yet have, would resolve the singularity into something less pathological. Perhaps a region of very high but finite curvature. Or perhaps something entirely different that we cannot currently imagine. Near the event horizon of a black hole, gravitational time dilation becomes extreme, and a distant observer watching something fall toward the horizon would see it slow down and freeze, appearing to take forever to cross the horizon. Though from the perspective of the falling object, time passes normally, and it crosses the horizon in a finite amount of its own time. And this difference in perspectives is one of the strange features of black holes. There is no single objective answer to questions like, has the object crossed the horizon yet? Because the answer depends on the observer's frame of reference. Black holes also have the property that they are characterized by only a few numbers: their mass, their spin, and their electric charge. And all other information about what formed the black hole, what kind of star collapsed, what was its composition, what was its detailed structure, all of this is lost, erased. And this loss of information is troubling from the perspective of quantum mechanics, which generally assumes that information is conserved, that the complete state of a system at one time determines its state at all future times. And the apparent loss of information in black holes has led to intense debates about the black hole information paradox, which remains unresolved, though various proposals have been made, including the idea that information is somehow encoded in the event horizon, or radiated away in subtle quantum effects. Hawking radiation and black hole evaporation. As we drift through our contemplation of black holes, let us now explore one of the most remarkable discoveries in theoretical physics. Stephen Hawking's prediction that black holes are not entirely black, but emit a faint thermal radiation due to quantum effects near the event horizon, and that this radiation causes black holes to gradually lose mass and eventually evaporate completely over enormously long timescales. Hawking radiation arises from a quantum phenomenon in which particle-antiparticle pairs spontaneously appear from the vacuum. Normally, these pairs quickly annihilate each other, but near the event horizon of a black hole, it can happen that one particle falls into the black hole while the other escapes. And from the perspective of a distant observer, the escaping particle appears as radiation emitted by the black hole, even though nothing actually came out from inside the event horizon. And the energy for this radiation comes from the black hole's mass, slowly draining it, causing the black hole to evaporate. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Larger black holes are colder, emitting less radiation, while smaller black holes are hotter, emitting more radiation, and for a stellar mass black hole, the temperature is incredibly low, only about 1/millionth of a degree above absolute zero, far colder than the cosmic microwave background. And so such black holes are actually absorbing more radiation from the cosmic microwave background than they emit through Hawking radiation, and they are growing, not evaporating. But as the universe expands and the cosmic microwave background cools, eventually the temperature of the cosmic microwave background will fall below the Hawking temperature of even large black holes, and they will begin to evaporate, though this will take an unimaginably long time. A solar mass black hole would take about 10 to the 67 years to evaporate completely, far longer than the current age of the universe, which is only about 10 to the 10 years. Smaller black holes evaporate faster, and in the final stages of evaporation, as the black hole's mass decreases, its temperature increases, and the evaporation accelerates, ending in a final burst of radiation. And if primordial black holes, hypothetical black holes that formed in the very early universe and that could have a wide range of masses, exist, then the ones with masses around 10 to the 15 grams would be evaporating right now, and their final bursts might be detectable as gamma ray sources, though no such events have been conclusively observed. Hawking radiation is a purely theoretical prediction, derived from combining quantum field theory and general relativity in a semi-classical approximation, and it has never been directly observed because the effect is far too weak for any black holes we know of. But it is widely accepted by physicists because the theoretical arguments are compelling, and because Hawking radiation resolves some puzzles about the thermodynamics of black holes. Specifically, it explains why black holes have entropy, a measure of disorder or missing information. And it provides a mechanism by which black holes can come into thermal equilibrium with their surroundings. The prediction of Hawking radiation also deepens the black hole information paradox. Because if black holes eventually evaporate completely, releasing their mass as radiation, then what happens to the information about the matter that fell into the black hole? If the radiation is purely thermal, containing no information, then the information is lost, violating quantum mechanics. But if the radiation carries information, then it must be encoded in incredibly subtle correlations between the emitted particles, correlations that we do not currently understand how to calculate or detect. And this paradox remains one of the most important open questions in theoretical physics, sitting at the intersection of quantum mechanics, general relativity, and thermodynamics. And its resolution may require a complete theory of quantum gravity that goes beyond both general relativity and standard quantum field theory, traveling near light speed. Let us imagine now what it would be like to actually travel at speeds approaching the speed of light, to experience firsthand the strange relativistic effects we have been discussing. The time dilation, the length contraction, the shifts in appearance of the stars and galaxies around us. And let us consider the practical challenges that would face any attempt to build a spacecraft capable of such velocities. As a spacecraft accelerates toward the speed of light, the energy required to continue accelerating increases without bound, approaching infinity as the speed approaches c. And this makes it effectively impossible to reach the speed of light itself, no matter how powerful the engines or how much fuel is carried. But speeds of 90 or 95 or even 99%, the speed of light might be achievable in principle, though they would require enormous amounts of energy and technologies far beyond what we currently possess. From the perspective of travelers on such a relativistic spacecraft, many strange effects would be noticeable, one of the most dramatic being the aberration of starlight. The apparent change in the positions of stars due to the spacecraft's high velocity. Stars ahead of the spacecraft would appear to concentrate toward the direction of motion, while stars behind would spread out, and the entire star field would appear distorted, with the universe ahead appearing compressed and the universe behind appearing stretched. Additionally, the light from stars ahead would be blue shifted, appearing brighter and shifted toward higher frequencies, while light from stars behind would be red shifted, appearing dimmer and shifted toward lower frequencies. And these effects would become more pronounced as the spacecraft's velocity increased. Eventually, stars ahead could be shifted into the ultraviolet or even X-ray portion of the spectrum, becoming invisible to the eye but potentially dangerous sources of high-energy radiation. From the perspective of observers on Earth watching the spacecraft depart, the most noticeable effect would be time dilation. The spacecraft's clocks would appear to run slow, and the travelers would appear to age slowly. And if the spacecraft traveled to a distant star and back at 99% the speed of light, the travelers might experience only a few years of subjective time, while decades or even centuries passed on Earth, depending on the distance traveled. And this is a real effect, not an illusion. The travelers would genuinely have experienced less time, would have fewer memories, fewer heartbeats, fewer thoughts. They would return younger than they would have been if they had stayed on Earth. And this one-way time travel into the future is an inevitable consequence of special relativity. The practical challenges of near-light-speed travel are enormous. Beyond the energy requirements, there are also problems with radiation at high velocities. Even the thin gas and dust that fills interstellar space becomes a dangerous source of radiation. Individual atoms striking the spacecraft at nearly the speed of light would have enormous energies, equivalent to high-energy cosmic rays, and shielding against this radiation would be very difficult, requiring thick barriers or electromagnetic deflection systems. Additionally, even tiny particles, dust grains or meteoroids, would have devastating impacts at such velocities, carrying kinetic energies equivalent to large explosions. And any collision could destroy the spacecraft. So extensive forward shielding and sophisticated navigation systems would be essential to detect and avoid obstacles. Despite these challenges, relativistic space travel remains a fascinating possibility. And if humanity's descendants someday develop the technology to build such spacecraft, they could explore the galaxy, visiting distant stars and witnessing cosmic phenomena firsthand. Though the time dilation means that they would be separated from their home civilization, not just by distance, but also by time. Travelers might return to find that centuries or millennia had passed on Earth, that civilization had changed beyond recognition, or perhaps had disappeared. And this temporal isolation is both one of the most interesting and one of the most troubling aspects of relativistic space travel. Faster than light and its impossibilities. Let us now contemplate what would happen if faster-than-light travel were possible, exploring the paradoxes and contradictions that would arise, and understanding why the speed of light as an absolute limit is not just a law of physics, but a fundamental requirement for the logical consistency of the universe. If an object could travel faster than light, it would be possible to construct scenarios that violate causality, where effects precede their causes, and one of the clearest ways to see this is through a thought experiment involving faster-than-light signals. Imagine that Earth and a distant star have synchronized clocks. And imagine that someone on Earth sends a faster-than-light signal to the star, a signal that travels instantaneously in Earth's reference frame, arriving at the star at the same time it was sent according to Earth's clocks. Now imagine that the star immediately sends a similar faster-than-light signal back to Earth, again traveling instantaneously in the star's reference frame. From Earth's perspective, the return signal arrives at the same time the original signal was sent. But now consider the same sequence of events from the perspective of a spacecraft moving at high velocity, relative to both Earth and the star. Due to the relativity of simultaneity, events that are simultaneous in one reference frame are not simultaneous in another. And depending on the spacecraft's velocity and direction, the return signal from the star could arrive at Earth before the original signal was sent. In the spacecraft's reference frame, the sequence of events is reversed. The reply comes before the message. And this creates a causal loop where the signal is its own cause, allowing for paradoxes like sending a message to your past self, instructing you not to send the message, a logical contradiction that cannot be resolved within the framework of special relativity. This thought experiment shows that faster-than-light travel or communication is fundamentally incompatible with special relativity and with causality. And any theory that allows superluminal signaling must either give up relativity, returning to an absolute notion of time that special relativity has shown to be incorrect, or must give up causality, allowing effects to precede causes and accepting the paradoxes that result. And neither option is attractive to physicists. There have been proposals for ways to circumvent the light-speed barrier without violating relativity, the most famous being the concept of a wormhole, a hypothetical tunnel through space-time that connects two distant regions, allowing travel between them without actually exceeding the speed of light locally. But passing through the wormhole could effectively allow faster-than-light travel in the sense that you could reach a distant location faster than light traveling through normal space could reach it. However, wormholes, if they exist at all, would likely be extremely unstable, collapsing before anything could pass through, unless they were held open by exotic matter with negative energy density. And it is not clear whether such matter can exist. Quantum field theory allows for negative energy densities in certain situations. But whether enough negative energy can be collected and maintained to keep a wormhole open is highly uncertain. And even if traversable wormholes could be created, they might immediately allow for time travel and causal paradoxes, and the laws of physics might prevent their creation for this reason. A conjecture known as the chronology protection hypothesis, proposed by Stephen Hawking, which suggests that the universe does not allow closed time-like curves, paths through space-time that loop back on themselves, connecting the past and future in ways that would permit time travel and paradoxes. The speed of light as a cosmic speed limit is thus deeply connected to the structure of causality and to the logical consistency of reality. And while we can imagine worlds with different physics where faster-than-light travel is possible, such worlds would be very different from ours, perhaps lacking the stable causal structure that makes science and reasoning possible. The arrow of time and entropy. As we drift through our exploration of how the speed of light shapes reality, let us now consider how the finite speed of light relates to another fundamental aspect of time, its apparent arrow. The fact that time has a direction, that processes have a preferred temporal ordering, that we remember the past but not the future, that things age and decay but do not spontaneously rejuvenate, and that entropy, a measure of disorder, always increases in closed systems, never decreases. The arrow of time is one of the deepest mysteries in physics, for the fundamental laws of physics, including both special and general relativity and the equations of quantum mechanics, are time-symmetric. They work equally well whether time runs forward or backward. And yet our experience of time is deeply asymmetric, and this asymmetry is related to the second law of thermodynamics, which states that entropy increases over time, that disorder tends to increase, that systems evolve from more ordered states to less ordered states, and that this process is irreversible. You can scramble an egg, but you cannot unscramble it. You can burn wood to produce ash and smoke, but you cannot reverse the process to recreate the wood. And these irreversible processes define a direction for time, an arrow pointing from past to future. The origin of the arrow of time is subtle and is related to the fact that the universe began in a very special, highly ordered, low-entropy state at the Big Bang. And ever since then, entropy has been increasing. Systems have been evolving from order to disorder. And this increase in entropy is what gives time its direction, what distinguishes past from future. And the fact that we remember the past but not the future is a consequence of this entropy increase. Memories are low-entropy configurations of information in our brains, and they form as a result of past interactions, but not future interactions. The finite speed of light contributes to the arrow of time in subtle ways, particularly through the concept of light cones and causal structure. For the past light cone of an event contains all the events that could have influenced it, all the information that could have arrived at the event traveling at or below the speed of light. And this defines a kind of causal past, a region of space-time that is accessible to the event. While the future light cone contains all the events that could be influenced by the event. And this defines a causal future, and the fact that influence can only propagate forward in time, from past light cone to future light cone, is part of what gives time its arrow. What distinguishes past from future, and what ensures that causality is preserved. The connection between entropy and the speed of light is also manifest in the phenomenon of black hole entropy, for black holes have enormous entropy, proportional to the area of their event horizons, and when matter falls into a black hole, its entropy is not lost but is added to the black hole's entropy, and eventually, through Hawking radiation, this entropy is radiated away. But the process is slow, and the radiation is highly disordered, thermal radiation with maximum entropy. And this ensures that the second law of thermodynamics is preserved. Even in the presence of black holes, entropy continues to increase, or at best remains constant, never decreases. The arrow of time and the increase of entropy are intimately connected to our subjective experience of reality, to our sense of agency and causality, to the flow of consciousness from moment to moment. And while the fundamental laws of physics are time-symmetric, the universe we inhabit is deeply time-asymmetric, with a clear direction from past to future, from order to disorder, from low entropy to high entropy. And understanding this asymmetry, understanding why time has an arrow and why it points in the direction it does, remains one of the great challenges in physics, touching on cosmology, thermodynamics, quantum mechanics, and perhaps even on the nature of consciousness itself, light, and the structure of space-time. Let us drift now into a deeper meditation on the fundamental relationship between light and space-time. Recognizing that light is not merely something that travels through space-time, but is intimately connected to space-time's very structure. For the paths of light rays, the null geodesics, define the causal structure of space-time, determining which events can influence which other events. And in a sense, the geometry of space-time is tailored to ensure that light always travels at the same speed in all reference frames. This deep connection between light and space-time is encoded in the metric of space-time, a mathematical object that specifies distances and time intervals between events. And this metric is constructed in such a way that light rays have zero length in space-time. They travel along null geodesics, where the space-time interval is zero, combining space and time in such a way that the speed always comes out to be c, regardless of who is measuring it. In special relativity, the metric is the Minkowski metric, a simple flat space-time metric, while in general relativity, the metric can be more complicated, curved by the presence of mass and energy. But in all cases, the metric preserves the property that light travels at c, and this constancy is built into the very fabric of spacetime. The profound connection between light and spacetime suggests that in some sense, light defines spacetime, or at least defines its causal structure. And this insight is taken very seriously in theoretical physics, where researchers studying quantum gravity often focus on understanding how the causal structure of spacetime emerges from more fundamental quantum processes. And some approaches to quantum gravity, like causal set theory, take the causal relationships between events as the primary reality, more fundamental even than spacetime itself, with spacetime emerging as an approximation or effective description when many causal relationships are present. The role of light in defining spacetime is also evident in the equivalence between inertial frames in special relativity, frames related by boosts, transformations that change velocity but not acceleration, and the fact that all inertial frames are equivalent, that no frame is privileged, is guaranteed by the constancy of the speed of light. And this equivalence leads to the symmetry group of special relativity, the Poincaré group, which includes translations, rotations, and boosts. And this symmetry is fundamental to all of particle physics and quantum field theory. General relativity extends this idea, replacing the flat Minkowski spacetime of special relativity with curved spacetimes that can have arbitrarily complicated geometries. But even in curved spacetime, the local structure is always close to Minkowski spacetime, a fact expressed by the equivalence principle, which states that in any small region of spacetime, in a freely falling reference frame, the laws of physics are those of special relativity. Gravity can be made to disappear locally by choosing the right frame. And this local flatness ensures that light always travels locally. At the speed c, though globally, in curved spacetime, light rays can be bent and delayed by the curvature. The speed of light is thus woven into the fabric of spacetime at the deepest level. It is not an arbitrary constant that happens to have a particular value, but is a structural feature of spacetime itself, a defining aspect of how space and time combine and how causality works. And any attempt to understand reality, to build theories of physics, or to comprehend the nature of the universe, must take the speed of light and its constancy as a fundamental starting point, a non-negotiable feature of the world that constrains and shapes all other phenomena, the observable universe and cosmic horizons. Let us now drift to consider the implications of the finite speed of light for what we can observe and what we can know about the universe. For the fact that light travels at a finite speed means that there are limits to how far we can see, and these limits create cosmic horizons beyond which we cannot observe, regions of the universe that are forever inaccessible to us, not because they do not exist, but because their light has not had time to reach us, or because they are receding from us so fast that their light can never reach us. The observable universe is the region of space from which light has had time to reach us since the Big Bang. And because the universe is about 13.8 billion years old, and because light travels at a finite speed, the observable universe is finite in extent. A sphere centered on Earth with a radius that corresponds to the distance that light could have traveled in 13.8 billion years. though this distance is actually larger than 13.8 billion light-years because the universe has been expanding while the light was traveling, carrying the emitting galaxies farther away. And the current size of the observable universe is about 93 billion light-years in diameter, with us at the center of our observational sphere. Though of course observers in other galaxies would see themselves at the center of their own observable universes. And there is no unique center to the universe as a whole. Every point is equivalent. Beyond the observable universe, there is presumably more universe, more galaxies and stars and planets. But their light has not had time to reach us yet. And if the expansion of the universe continues, as it appears to be doing, then some of these distant regions will never become observable, no matter how long we wait, because they are receding from us faster than light can approach us through the expanding space. And they will forever remain beyond our horizon, invisible and unknowable. This horizon is not a physical boundary, but an observational limit. And it is constantly expanding as time passes and as light from more distant regions has more time to reach us. But if the expansion of the universe continues to accelerate due to dark energy, then there is also a future horizon, called the cosmic event horizon, beyond which events happening now will never be observable by us, no matter how long we wait, because the expansion will carry those events away from us faster than their light can reach us. And this event horizon is actually getting closer to us over time, in the sense that galaxies that are currently just inside the event horizon will cross outside it in the future, disappearing from our observable universe. And eventually, if the acceleration continues, we will be left with only our local group of galaxies, all gravitationally bound together, while the rest of the universe recedes beyond the horizon. And distant observers will see the same thing from their perspectives, each local group becoming an island universe, causally disconnected from all others. These cosmic horizons are a direct consequence of the finite speed of light combined with the expansion of the universe, and they have profound implications for cosmology and for what we can know about the universe. For if there are regions forever beyond our horizon, then there are questions about the universe that we can never answer through observation. Questions about what exists in those regions, whether the laws of physics are the same there, whether there are other forms of life or intelligence. And these questions may be intrinsically unanswerable, not because of any limitation of our technology or intelligence, but because of the fundamental structure of space-time and the finite speed at which information can propagate. Quantum entanglement and faster-than-light correlations. As we drift deeper into the mysteries of light and reality, let us now explore one of the most puzzling phenomena in quantum mechanics, entanglement, where two particles can be connected in such a way that measuring one instantly affects the other, no matter how far apart they are. And this apparent faster-than-light connection has troubled physicists since the early days of quantum mechanics, leading Einstein to call it spooky action at a distance, and to argue that quantum mechanics must be incomplete. Quantum entanglement occurs when two particles are created together or interact in such a way that their quantum states become correlated, so that measuring a property of one particle, such as its spin, instantly determines the corresponding property of the other particle, even if the particles are light years apart. And this correlation is not due to the particles carrying hidden information that was determined when they were created, but is a genuine quantum phenomenon where the properties of the particles are not determined until they are measured. And the measurement of one particle instantaneously collapses the quantum state of both particles, determining the outcomes. This seems to violate special relativity, to allow faster-than-light influence. But in fact, it does not, because the correlations cannot be used to send information faster than light. The measurement outcomes at each location appear random, and it is only when the results from both locations are brought together and compared, a process that requires communication at or below the speed of light, that the correlations become apparent. The no communication theorem proves that entanglement cannot be used for superluminal communication. And so while entanglement involves correlations that are established faster than light, it does not actually transmit information faster than light, and causality is preserved. Nevertheless, entanglement is deeply strange and challenges our classical intuitions about locality and separability, the ideas that objects have definite properties independent of measurement, and that distant objects cannot influence each other instantaneously. Bell's theorem, proved by John Bell in 1964, shows that no theory based on local hidden variables, where particles carry predetermined values for all their properties, and where influences can only propagate at or below the speed of light, can reproduce all the predictions of quantum mechanics. And experiments testing Bell's theorem have consistently confirmed the quantum predictions, ruling out local hidden variable theories and showing that entanglement is a real feature of nature, not a defect or incompleteness in quantum mechanics. The resolution to this apparent conflict with relativity is subtle. Entanglement does not violate relativity, because it does not allow for the transmission of information or the violation of causality. But it does show that the world is non-local in a certain quantum sense, that distant parts of an entangled system are connected in ways that cannot be explained by any classical mechanism involving signals traveling between them. This non-locality is one of the most profound and mysterious aspects of quantum mechanics, and it raises deep questions about the nature of reality, about what it means for something to be real or to have definite properties, and about how quantum mechanics relates to space-time and relativity. Some interpretations of quantum mechanics, like the many worlds interpretation, attempt to explain entanglement without invoking non-locality, by suggesting that all measurement outcomes occur in different branches of a vast multiverse. While other interpretations, like the de Broglie-Bohm pilot wave theory, embrace non-locality explicitly, allowing for faster-than-light influences that are carefully arranged so as not to allow superluminal communication. And the debate over the correct interpretation continues, with no consensus among physicists, though all agree on the experimental predictions, which are unambiguous and well confirmed. The speed of light in different media. Let us drift now into a more practical aspect of light's behavior. The fact that while the speed of light in vacuum is constant and represents an absolute cosmic speed limit, the speed of light in material media, in water or glass or air, is slower than c. And this slowing occurs because light interacts with the atoms and molecules of the material, being absorbed and re-emitted many times as it propagates, and each absorption and re-emission takes a tiny amount of time, causing the overall progression of the light wave through the material to be slower than it would be in vacuum. The speed of light in a material is characterized by the material's refractive index, defined as the ratio of the speed of light in vacuum to the speed of light in the material. So a refractive index of 1.5 means that light travels 1.5 times slower in the material than in vacuum. And different materials have different refractive indices. Water has a refractive index of about 1.33, meaning light travels about 25% slower in water than in vacuum, while diamond has a refractive index of about 2.42, meaning light in diamond travels at less than half its vacuum speed. The slowing of light in media has many practical consequences. It is responsible for refraction, the bending of light rays when they pass from one medium to another with a different refractive index. And refraction is the basis for how lenses work, focusing light to form images and for phenomena like rainbows, where sunlight is refracted and dispersed by water droplets in the atmosphere, separating into its component colors because different wavelengths of light have slightly different refractive indices and are bent by different amounts. An interesting consequence of the fact that light slows down in materials is that it is possible for particles to travel through the material faster than light travels through that material, though still slower than the vacuum speed of light. And when this happens, the particle emits a cone of light called Cherenkov radiation, similar to the sonic boom produced by an object moving faster than sound. And Cherenkov radiation is observed in nuclear reactors, where high-energy particles produced by nuclear reactions travel through water faster than light travels through water, creating a characteristic blue glow. The fact that light slows down in materials also means that the cosmic speed limit, the absolute maximum speed that is built into the structure of space-time, is specifically the speed of light in vacuum, not the speed of light in materials, and this distinction is important because it preserves the special status of Ci as a fundamental constant that enters into the equations of relativity and that determines the causal structure of space-time. In vacuum, nothing with mass can reach the speed c, and nothing with or without mass can exceed it. But in materials, it is possible for massive particles to temporarily exceed the local speed of light, though they still cannot exceed the vacuum speed of light. And this possibility does not violate relativity or causality, because the relevant speed limit for these purposes is always the vacuum speed, not the material speed. The behavior of light in media is described by classical electromagnetism, Maxwell's equations, combined with a description of how the material responds to electromagnetic fields. And this classical description works extremely well for most purposes, but at very high intensities or very short timescales, the quantum nature of light and matter becomes important, and more sophisticated quantum theories are needed to fully describe the interaction of light with materials, visualizing four-dimensional space-time. As we near the end of our long drift through the speed of light and its consequences, let us attempt to visualize the four-dimensional space-time that special and general relativity describe. For while we cannot directly perceive four dimensions, living as we do in a three-dimensional spatial world moving through time, we can use analogies and mathematical representations to gain some intuition for how space-time works. The key idea is that space-time is a single unified entity, not two separate things, space and time. And events are points in this four-dimensional continuum, specified by three spatial coordinates and one time coordinate. And the history of an object traces out a world line, a curve through space-time that shows where the object is at each moment of time. One helpful analogy is to think of space-time as similar to a physical space, but with one of the dimensions being time. And to visualize space-time diagrams, graphs where one or two spatial dimensions are plotted on the horizontal axis and time is plotted on the vertical axis. And world lines of objects appear as curves on these diagrams. Vertical lines for objects at rest, diagonal lines for objects moving at constant velocity, and curved lines for accelerating objects. And the world lines of light rays always make 45-degree angles with the time axis, reflecting the fact that light travels 1 unit of distance per unit of time. When we use units where the speed of light is 1, the light cone at any point in space-time consists of all the light rays passing through that point, forming a double cone with the point at the center. The future light cone extending upward toward future times, and the past light cone extending downward toward past times. And these light cones divide space-time into regions. Events inside the future light cone can be influenced by the central event. Events inside the past light cone can influence the central event. And events outside the light cone are space-like separated from the central event and cannot be causally connected to it. In general relativity, where space-time can be curved, visualizing the geometry becomes more challenging. But we can use the rubber sheet analogy, where space-time is represented as a flexible two-dimensional surface. And massive objects create indentations in this surface, curving it, and other objects follow the curves, rolling along geodesics that look like orbits or falling trajectories. Though this analogy is limited because it shows only two spatial dimensions, and because it uses a three-dimensional embedding space to visualize the curvature, while actual space-time curvature is intrinsic, existing without any need for a higher dimensional space to curve into. Despite these limitations, space-time diagrams and analogies can help build intuition for relativistic phenomena, showing how time dilation corresponds to worldlings that are tilted relative to each other, how length contraction corresponds to different slicing of space-time into space and time, and how the relativity of simultaneity means that different observers have different notions of which events are happening. Now, corresponding to different horizontal slices through the space-time diagram. The mathematical description of space-time uses tensor calculus, a sophisticated branch of mathematics that allows for precise calculations in curved spaces. And while the mathematics can be intimidating, the physical insights are often surprisingly intuitive once the basic concepts are understood. And many of the predictions of relativity, such as time dilation and length contraction, can be derived from relatively simple geometric arguments once one accepts the constancy of the speed of light and the principle of relativity. The four-dimensional space-time of relativity is not just a mathematical abstraction, but is the arena in which all physical processes occur. And understanding space-time, understanding how space and time are interwoven and how they are affected by matter and energy, is essential to understanding the universe at a deep level. And this understanding, which began with Einstein's recognition of the profound implications of the constant speed of light, has revolutionized physics and continues to shape our investigations into the nature of reality. Philosophical implications of the speed of light. As we drift toward the conclusion of our journey, let us reflect on the deeper philosophical implications of the speed of light and its role in shaping reality. For the constancy of light speed and the resulting structure of space-time have profound consequences not just for physics, but for how we understand the nature of reality, causality, determinism, and our place in the cosmos. The finite speed of light means that we never perceive the present state of distant objects, but only their past. We see the sun as it was 8 minutes ago, the nearest star as it was over 4 years ago, distant galaxies as they were billions of years ago, and in a sense, the present moment, the now that we experience, is a local phenomenon, limited to our immediate vicinity, and there is no universal present that extends throughout the universe. Different observers have different notions of which distant events are happening now. And this relativity of simultaneity challenges our intuitive sense that the universe exists in a single definite state at each moment of time, evolving from one state to the next in a universal sequence. Instead, space-time presents us with a four-dimensional whole, sometimes called the block universe, in which all events past, present, and future exist together, and the flow of time, the sense that we are moving from past through present to future, is a feature of our consciousness, of how we perceive and remember, rather than a fundamental feature of reality itself. Though this is a matter of philosophical debate, and not all physicists or philosophers accept the block universe interpretation. The speed of light also constrains what can affect what, creating the causal structure that ensures effects follow causes and that prevents paradoxes. And this causal structure is fundamental to our ability to reason about the world, to perform science, to make predictions and test them. For if causality were violated, if effects could precede causes, then the logical foundation of science would crumble, and the world would be unintelligible. Actions could have consequences in the past that prevent the actions from occurring. And such self-contradictory scenarios cannot be part of a consistent reality. The fact that nature respects causality, that the universe is structured in such a way that these paradoxes do not occur, is remarkable and suggests that there may be deep principles, perhaps related to quantum mechanics or to thermodynamics or to some deeper theory we do not yet have, that enforce consistency and that prevent the universe from falling into logical contradiction. The speed of light also limits our sphere of influence. We can only affect events within our future light cone, and we can only be affected by events within our past light cone, and this locality, this limitation of influence to nearby regions, is intimately connected to the structure of causality and to the conservation laws of physics. Conservation of energy, momentum, angular momentum, and other quantities all rely on locality, on the idea that changes propagate continuously through space at finite speeds. And if faster than light influences were possible, these conservation laws might be violated. Another reason to believe that the cosmic speed limit is fundamental and inviolable. The unification of physics. As we continue to drift through these final contemplations, let us consider how the speed of light connects to the larger project of unifying physics, of finding a single theoretical framework that encompasses all the fundamental forces and particles, and that explains the deepest principles that govern reality. Special relativity unified space and time into space-time, and it unified the electric and magnetic fields into the electromagnetic field, showing that electricity and magnetism are aspects of a single phenomenon. And this unification was a major achievement, but it was only the beginning. General relativity unified space-time with gravity, showing that gravity is not a force acting through space, but is the curvature of space-time itself. And this was another profound unification. But gravity remains separate from the other forces. The electromagnetic force, the weak nuclear force, and the strong nuclear force, which are described by quantum field theories that have been unified into the standard model of particle physics. A quantum theory that explains all non-gravitational phenomena in terms of particles and fields and quantum interactions. And the standard model has been enormously successful, explaining vast ranges of phenomena and making predictions that have been confirmed to extraordinary precision. But it does not include gravity, and attempts to create a quantum theory of gravity have faced profound difficulties. The speed of light appears in both relativity, as the speed that determines the causal structure of space-time, and in quantum field theory, as the speed at which massless particles like photons must travel, and as the speed that sets the scale for relativistic effects in particle physics. And so the speed of light is a bridge between these two great frameworks, and any successful unification of quantum mechanics and gravity, any theory of quantum gravity, will need to respect the constancy of the speed of light and the causal structure it creates. Various approaches to quantum gravity have been proposed: string theory, loop quantum gravity, causal set theory, and others. And each attempts in its own way to reconcile quantum mechanics with general relativity, to describe space-time and matter at the smallest scales, where both quantum effects and gravitational effects are important. And these approaches often lead to radical new ideas about the nature of space and time and reality, suggestions that space-time is not fundamental, but emerges from something more basic, that space and time are quantized, that there are extra dimensions beyond the three of space and one of time that we experience, and many other exotic possibilities. But despite decades of work, no approach has yet achieved a complete and verified unification. And the quest continues, driven by both theoretical puzzles, like the incompatibility of quantum mechanics and general relativity, and by observational mysteries, like the nature of dark matter and dark energy, and perhaps the ultimate theory, when it is found, will reveal new insights into the speed of light and its role in the structure of reality, showing it to be even more fundamental, or perhaps less fundamental than we currently believe, derived from some deeper principle. But whatever the ultimate theory turns out to be, the speed of light will remain a central element, a constant that has shaped our understanding of the universe and that will continue to guide us as we probe deeper into the nature of existence, letting go into the cosmic night. As we prepare to complete our journey, drifting now into the final stages of rest and contemplation, let us release our grip on the details we have explored tonight and allow them to settle into the background of awareness, becoming part of the deeper understanding that does not require conscious effort to maintain. The speed of light, with all its strange consequences for time and space and causality, is not something you need to fully comprehend in order to rest peacefully. It is enough to have touched these ideas, to have drifted through them like a traveler moving through a vast landscape, seeing the features but not needing to map every detail. And now, as you sink deeper into comfort, breathing slowly and evenly, you can let the concepts dissolve, returning to the simple direct experience of being, of existing in this moment, without needing to understand or analyze or remember. The universe is vast and strange, governed by laws that transcend our everyday intuition. And the speed of light is woven into the fabric of reality in ways that shape everything, from the smallest quantum interactions to the largest cosmological structures, from the flow of time to the limits of what we can know and where we can go. And this is beautiful. This is profound. And it is also okay to not think about it right now, to simply be here, breathing, resting, allowing sleep to come naturally and gently as it will. The light from distant stars has been traveling toward us for years or centuries or millennia, crossing the vast, empty spaces between suns. And when it finally reaches your eyes on a clear night, you are seeing the past, connecting across time with events that happened long ago. And this connection, this thread of light linking past and present, is one of the ways we are connected to the cosmos. One of the ways that despite our smallness and brevity, we are part of something immense and enduring. You rest now. You can imagine yourself as a point in space-time, your world line extending from your birth through this present moment and onward into the future, tracing a path through the four-dimensional fabric, and all around you, other worldlings, of other people, of objects, of particles of light streaming through space at their constant speed. All these world lines weaving together to form the tapestry of reality. And you are part of this. You are one thread among countless trillions, and your thread is important. It matters. It is real, and it is also temporary, a finite curve with a beginning and an end. And this temporariness is okay. It is natural. It is how the universe works. And accepting it, accepting your place in the flow of time, can bring a kind of peace, a release from the need to hold on too tightly to things that must pass. The eternal now. As we drift deeper into rest, let us contemplate one final paradox: the relationship between the flowing time we experience and the eternal space-time of relativity. For while relativity suggests that all moments exist equally, that past and future are laid out in the four-dimensional block universe as real as the present, our experience is of a single moving present, a now that is always here, always immediate. And this now is where we live, where we feel and think and act. And this subjective present is real, even if it is not fundamental to the physics. It is the arena of consciousness, the stage on which experience unfolds. Perhaps the resolution to this paradox is that both views are valid. space-time as an eternal four-dimensional whole from the perspective of physics and mathematics, and time as a flowing river from the perspective of experience and consciousness. And neither view is more true than the other. They are complementary aspects of reality, different ways of understanding the same underlying truth. As you rest here in this present moment, breathing gently, feeling the weight of your body supported by the surface beneath you, you are experiencing the now, the only moment that exists from your subjective perspective. And this moment is enough. It contains everything you need. There is nowhere else you need to be, nothing else you need to do. Just this breathing, this resting, this simple existence in the present. And from the perspective of space-time, this moment is just one slice through the four-dimensional whole, no more or less real than any other moment. But from your perspective, it is everything. It is all there is. And both perspectives are true. Drifting into sleep. And now, as we reach the end of our journey together through the speed of light and its implications for reality, it is time to let go completely, to release all thoughts about light and time and space and causality, to allow your mind to become quiet and still, to drift into the peaceful emptiness that precedes sleep. You have traveled far tonight, from the constancy of light's speed through time dilation and length contraction, through the cosmic speed limit and the structure of space-time, through black holes and gravitational waves, through all the strange and beautiful consequences that flow from this one fundamental fact about the universe: that light always travels at the same speed, regardless of who measures it. And this simple statement has broken our reality, has shown us that time is not absolute, that space can contract, that mass and energy are equivalent, that nothing can travel faster than light, that simultaneity is relative, that the universe has horizons beyond which we cannot see. And all of this is true, all of this is real. But right now, in this moment, you do not need to think about any of it. You can simply rest. Can let yourself sink deeper into comfort with each breath. Your body becoming heavier and more relaxed. Your mind becoming quieter and more peaceful. Thoughts drifting away like clouds, dispersing in a clear sky, leaving only awareness, only being, only the simple fact of existence. And even this awareness can fade now, can dissolve into sleep, into dreams or dreamlessness, into the deep rest that your body and mind need. And as you drift into sleep, know that the universe continues around you, light continuing to stream through space at its constant speed, time continuing to flow in its strange, relativistic way, space-time continuing to curve and flex in response to matter and energy, all the vast machinery of existence continuing to operate, and you are part of it. You are one small thread in this infinite tapestry, and right now your thread is at rest, is peaceful, is sleeping. And this is good. This is right. This is exactly as it should be. And so rest now, sleep now. Let go completely into the darkness, into the quiet, into the gentle embrace of night, and drift away on the currents of sleep. Floating like a photon through the cosmos, traveling at the speed of light through your own inner space, through the landscape of dreams and rest. And somewhere in that infinite darkness, you will find peace. You will find renewal. You will find the deep rest that allows you to wake refreshed and ready to face another day. But that is tomorrow. That is the future. And right now there is only this, only the present moment as it fades into sleep, only the gentle dissolution of consciousness into the void. And this is beautiful. This is natural. This is the way of all things. Rest and activity, waking and sleeping, light and darkness, all part of the eternal rhythm. And now it is time for darkness, time for rest, time for sleep, deep and peaceful and complete. And you can let go now, completely, finally, surrendering to the inevitable pull of sleep, falling gently into that warm, dark space where dreams live, or perhaps into the deeper darkness where even dreams do not reach. The darkness of pure rest, of consciousness released from the need to know or understand or experience, just being, just existing, and then not even that. Just sleep, just peace, just rest.